Chapter 4.5, Integration by Substitution. Day 1, Finding a Pattern. Up till now, all our antiderivatives have been pretty simple and straightforward. Today we're going to see a little bit more complexity in our antiderivatives. For differentiation, we've done something called the chain rule, where we start with a function inside of a function, and we work the derivative. We take the derivative of the outside function, keep the inside function inside, and then we take the derivative of the inside function on the outside of that. Well, today we look at the reverse of that. We're going to finish with that expression, and we're going to work backwards to our original function. All right? And that's called substitution. Now for substitution, what's key is we need to recognize that there is a function inside of a function. All right? To do substitution, recognize there's a function inside of a function. Now the function that's outside may just be x to the 1. But the other thing we need to recognize is that right next to it, there's the derivative of our inside function. Now it's not going to always be exactly a derivative, but it's going to be within a constant, meaning multiply or divide by a constant. So let's look at a few of these examples. Remember, we're going to look and try and recognize a function inside of a function. All right, so our first example, we want to recognize the pattern. Find the antiderivative of x squared plus 1 squared times 2x with respect to x. First off, recognize we have a function inside of the square, and that our derivative of that function is outside. All right? That means we can use substitution. Now to do substitution, I need to pull out my inside function. My inside function is x squared plus 1. So I'm going to substitute u in for x squared plus 1. So that means I'm changing the variables. I need to change the variable of everything, and that means I need to change the variable of dx as well. So that means I need to take the derivative of u. So the derivative of u with respect to x equals 2x. All right? Solve for du. So we got du by itself. That means multiply both sides by dx. We got du equals 2x dx. Now if we look at that, u is right here. So I'm going to replace x squared plus 1 with u. Also, if you happen to notice, right here, we got 2 dx. Oh, whoa, excuse me. Right here we got 2x dx. They're exactly the same. Anytime something's exactly the same, we can substitute. So I'm going to replace the 2x dx with du, because they're equivalent. So what we got when we substitute, x squared plus 1 becomes u. Don't forget your square. 2x dx becomes du. And that is a pretty simple, straightforward power rule antiderivative. Okay, the 2 goes up to become 3, divide by 3, plus a constant. Now in this case, we're not done here, because our question asks for with respect to x, and we have an answer with respect to u. So just put u back in. So our answer becomes 1/3 x squared plus 1 cubed plus a constant. All right, let's look at another example. All right, antiderivative 5 cosine 5x dx. What's our function inside of a function? Well, that is 5x. U equals 5x. du dx then will equal 5. Let's multiply both sides by dx. Eventually, you'll get to the point where you just do that automatically. Just say du equals 5 dx. All right, let's do our substitution now. U is 5x. Du is 5 dx. So that can be a straightforward substitution. So we got cosine of u, du. The antiderivative of cosine is sine. Sine of u plus a constant. Put u back in, sine of 5x plus a constant. All right, let's look at this one. This one is slightly different. All right, our function inside, first off, let me rewrite this as a fractional power. And our function inside is 2x minus 1. If we take the derivative of 2x minus 1, we get 2. So then du is 2 dx. All right, take a look at what we got. We got our 2x minus 1. We got dx, but we don't have the 2. All right, how do you deal with that? Well, it's not that difficult. All you do, we need a 2, you put a 2 in. So I'm going to multiply the expression by 2. However, I've changed it. How do you balance a change of multiplying by 2? Well, you can balance a change of multiplying by 2 by multiply by 1/2. Because 2 times 1/2 is 1. And I really just multiplied by 1, which doesn't change the expression. So now, the 2 is there. I got my 2x dx, which is really du. I got my 2x minus 1, which is going to be u. And I can go ahead and finish the problem. So it'll be 1/2 u to the 1/2 du. All right, power up, 1/2 goes to 3/2. Multiply by the reciprocal, so 2/3. 2/3 times 1/2 is 1/3 plus a constant. So we get 1/3 2x minus 1 to the 3/2 plus a constant. All right, what do we do when there's limits up there? Right? Meaning we got limits of integration from 0 to 1. How do we handle that? All right, so to handle that, we're going to do the same thing. We're going to take our antiderivative. We're going to do our u substitution. So let's see what happens. First off, our u is x squared plus 1. That means our du is 2x dx. I said you'd eventually do that. I'm going to start doing that right now, where I put the dx on the other side with the x right away. I need 2x. I have x, so I will multiply by 2 and multiply by 1/2 to keep it balanced. All right. Now as I substitute, I'll have 1/2. 2x dx is du. X squared plus 1 is u cubed. Now my limits are in terms of x. And I have an expression here that's in terms of u. So I need to convert my units, or my limits, from x to u. And all I do for that is I substitute. So I'll take this 0 right here, my lower limit, and I will substitute that into my u expression. 0 squared plus 1 is 1. So my new lower limit in terms of u is 1. My new upper limit, when I stick 1 into my substitution expression, 1 squared plus 1 is 2. My new upper limit in terms of u is 2. So what I need to do when I have limits is convert them from u, or from x, to u. Right? And as I do that, now I can integrate. U cubed becomes u to the 4th over 4 from 1 to 2. I can just pull the constants out. That leaves me 1/8 times 2 to the 4th is 16 minus 1 to the 4th is 1. So I am left with 15/8. Now the advantage of converting your units over to u is I don't have to convert this back to a longer expression. You don't have to convert the units to u. You could just leave it and then go back to x and then put in your original limits. But then you're going to be substituting it into x squared plus 1. It's going to be the same. It's going to be a longer process. So when you have limits, change them into the variable to match up. All right, so in review, first thing, you need to make an observation. Observe that you have a function inside of a function. And also observe that the derivative of that function, not exactly, but within a multiple of a constant, is outside of the function. All right? Then you're going to substitute out the inner function with u. Take your derivative of u with respect to x, solve to get du. Excuse me. Then you're going to substitute in du. Then you're going to integrate and put x terms back in.